Welcome to the McMaster's Forge, where our team does our blacksmithing and casting. It is outfitted with numerous safety features such as a gas detector and a 24/7 fume hood. During forging, at least 2 people must be present in the room. Ear and eye protection are mandatory, as well as long pants and closed-toed shoes. Our forge is a propane-fed furnace which can reach temperatures of up to 12,000 degrees Celsius. During forging, a glove is worn on the offhand to prevent burns. However, the hammer hand must be bare to ensure better control. For this project, the blade was forged from Raging 350, an iron nickel cobalt molybdenum alloy known primarily for its fracture toughness and strength. Our blade was made from round stock, courtesy of SSA. The first step was to taper one end to produce a tip. Then, it was flattened into an oval cross-section. Lastly, a cross-peen hammer was used to widen the blade and lengthen the tang. All forging was done completely by hand, and as such, it took many hours to complete. After forging, our blade was ground to its desired thickness of around 3 mm using a high-speed angle grinder, before a flat bevel profile was added using a more precise variable speed. Then, a triangular file was used to cut saw into the back at alternating angles to produce a cross-cut pattern. Our blade is based off the Case M-1 Astronaut Knife, which was used on 22 spaceflights and 9 trips to the moon. The knife was included as part of the survival kit, which contained essential items for an emergency landing into inhospitable terrain. Being a knife designed for astronauts, the design criteria was not only influenced by use of the survival knives on thick forests, but also by logistics of spaceflight. All of our samples were cut on a wire EDM at the McMaster machine shop. They were then solutionized and aged for various times to maximize fracture toughness while maintaining a minimum hardness of 54 HRC. For the first step of our mechanical testing, we first measured hardness using an analog hardness tester and discovered that even at short times, our minimum hardness was hit, resulting in us shortening our aging times. We then performed Sharpie testing to find Sharpie impact energy, making sure that 2 people were always present and body parts were never placed in the way of the testing head to ensure safe operation. The last tests which we performed were corrosion. As our blade could potentially face harsh coastal environments, we decided to perform a long-term saltwater immersion test. Both as-received and heat-treated samples were placed in a 3.5% aqueous sodium chloride solution for 430 hours, and then weighed to measure up mass loss and compare to literature values. After testing was complete, cross-sections were taken from the heat-treated Sharpie impact samples and hot matched. They were subsequently ground and polished using an auto polisher down to 1 micrometer diamond suspension to achieve a mirror finish. After polishing, the samples were cleaned with ethanol and then etched using a 2% nitol etchant in a fume hood with secondary containment. We found a significant variation in etching speed between our samples and could thus conclude that they exhibited a large variety of microstructures. After etching, we first took images of the etched samples and corrosion samples using a Keyence microscope. We then took SEM images of our samples using the Aprio 2S Lovac at the Canadian Centre for Electron Microscopy. Images were taken with backscatter electrons, secondary electrons, and EDS. A primary objective of the handle of our blade was that it could not off-gas and pollute the atmosphere during spaceflight. As such, we decided to make our handle out of cast A356 aluminum, using a modified lost wax casting method where PVB was used instead of wax. An aluminized suit and face shield were worn during casting to prevent burns and protect against splashes. The handle and blade were then drilled using a drill press and were secured together mechanically via 2 brass dowels, which were ball-peened to prevent movement. Connecting back to our success criteria, through our mechanical testing, material characterization, and finally our blade fabrication, our team was able to produce a blade that would confidently withstand the rigors of spacecraft.